Welcome everyone to today's webinar. My name is Elise Roberts. I'm an officer with the section on statistics in defense and national security. I am really excited to have Dr. Amanda Muyskens from Lawrence Livermore National Laboratory speaking for us today. Dr. Muyskens' expertise in data science includes surrogate modeling, Gaussian process models, computationally efficient machine learning, uncertainty quantification, and statistical consulting. She is currently leading MuyGPs exploratory research project that has developed a novel method for scalable non-stationary Gaussian processes for high-performance computing. She and her team have released a Python package that is available for download on GitHub. And one more thing, SDNS is soliciting entries for the section's student paper competition for next year's JSM. This competition is open to all undergraduate and graduate students, as well as researchers that are at least 2 years beyond their terminal degree. We request that entries be sent to Kim Caulfield by mid-December. And with that, I will hand it over to Dr. Muyskens to get started.
Thank you. And thank you so much for having me today to talk. I'm very excited to share some of the work that I've been doing at Lawrence Livermore National Lab with all of you. The method that I'm going to talk about today is called MuyGPs. It was named actually for the original, the last name initials for the original inventors, although we got very lucky that it was a Gaussian process method. It already included their GPs in the title. It was quite advantageous. So I'm very excited to talk to you about this today. Before we get going, I just want to give a little context of where Lawrence Livermore falls in this field of national security. We are one of the 3 major multi-purpose security labs, along with Los Alamos and Sandia. And along with our national security work, we do a host of other science that is both open and usually involves something having to do with high performance computing. We have some of the best supercomputers in the world. It's a very exciting place to be. Since I've been here, I've worked on, in a very short amount of time, all sorts of applications. And I would be amiss if I didn't say we have a great summer student program. And so applications for that should open in about November for next summer. And we're always looking to add people to our team in general, if any of these areas interest you. So the main area that has motivated this research, you may have noticed in my original graphic some stars. It's a very exciting time to be interested in looking and exploring our universe. We have a lot of tools that are coming online that are creating more data than we really know what to do with yet, to be honest. So the main tool that we are interested in is the Rubin Observatory, also known as LSST. That's going to be the largest and deepest space survey that's going to come online in just a few years. This data is going to create maybe about 20 terabytes approximately of sky pictures overnight, and this survey will go on for about 10 years. So we have to be able to have automatic methods that can sort reliably through this information. One reason, at least, there are many reasons why we'd want to look at these space surveys, is the connection to dark matter. So eventually we'd like to understand the pictures of the universe and compare them to simulations of the universe in order to understand the underlying parameters in maybe a Bayesian calibration sense of these parameters and how they behave, so we can better understand dark matter in the universe. There are a lot of other side goals along this process. So the first you're seeing here, this is just an example of what we expect the picture to sort of look like. On the left is pure data, and on the right is with the artificial noise added to the level we think it should be. We'd like to take these pictures. If you've ever seen some of the true pictures of the universe, and this is simulated data, of course, you might notice that there are sort of streaky areas or areas that don't look exactly straight on. And that process is called weak gravitational lensing. Basically, instead of looking at the universe as it appears when there's lots of matter, the light will bend. And so we're not seeing the exact picture of the universe the way that it actually exists. So we need to sort of reverse engineer that lens that we're looking through the universe at in order to begin to match these simulations to reality. And in order to even begin to do that, we have to understand where the matter lies. And that requires a problem, which I'm showing along the bottom here, of taking these cutouts of the objects in the universe, and they then classifying them as whether they're a star or a galaxy, so we could know maybe their relative mass. And so there's a host of problems that we need to do, and each step of these problems, we need to not just have a good estimate of them, but we need to know the uncertainty quantification in those predictions. So maybe whether we're certain about them. And the one reason we would want to do this is that there are limited human resources we can double check things. So let's say our model was very uncertain whether it was a star or a galaxy. We could have every night an astronomer check some small amount of these. We wouldn't want to waste our time going fishing in this 20 terabytes of data. We would not want to know where to focus our resources in order to change our outcome the best. This is a wide variety of problems, all of which need uncertainty quantification, but also machine learning methods as they exist currently are becoming computationally unscalable in order to process that large amount of data theoretically every night. This is not unique to this problem. Of course, this exists in all sorts of problems we deal with at the labs. In general, that computing resources is nearly doubling for state-of-the-art methods approximately every 3 to 4 months. And even with our planned exascale computing capabilities in the future, this is sort of an unsustainable level of machine learning, especially when we consider that machine learning and building these models is generally an iterative process. You don't just train it once and you're done. Typically, we have lots of give and take. It's too much computationally, so we need to take another approach. This is what generally motivated us to turn to develop MuyGPs. Our idea here is we're going to take a model, the Gaussian process, that is a well-known statistical model that didn't previously scale, or there were other scaling options. It's been a focus of the literature for a while in academia, none of which have scaled really to the quantities we need, something on the order of hundreds of millions to billions data points. But we need to keep that uncertainty quantification, which Gaussian processes have native. Previously, there was not a good way to parallelize this, although it was possible, it was rather clunky. So we've built a new HPC integration. And the last thing that we're focusing on is non-stationarity. So incorporating some more flexibility into the Gaussian process model, since some of the common assumptions are pretty harsh. So unlike other machine learning methods, we have this uncertainty quantification, and unlike other GPs in general, these tend to scale. And you will see it's very flexible. So this is MuyGPs. We sort of think of it more as a framework than a specific set of models, and it's more a general idea. I'm sure everyone knows this, since earlier in the series, I think Bobby Gramsci described what Gaussian processes were in detail, but I just want to make sure everyone's on the exact same page. A Gaussian process model is basically at its core an extension of the multivariate normal distribution, where any 2 points in the domain are assumed to be jointly normally distributed, any subset of points at that. Which basically means that we can write down the model only through a mean function and a covariance function. The mean function is usually written down as something relatively simple. Oftentimes it's 0. I would guard against that, particularly if you plan on doing any extrapolation or your correlation is very small, that actually can impact your results. So I would at least recommend using like a sample mean or something as this mean function. And the main idea of the Gaussian process model and why this is hard is that we have to estimate these parameters that have to do with the covariance matrix K. So I don't want to throw these equations are less important, more important that they exist. The idea being that the predictions and the prediction variances are exactly derivable from this distribution using conditional distributions. And they are both a function of those covariance parameters that you are essentially trying to estimate. Okay, so the function that we'll use is the Matern covariance. So this is the function in which you would put in the distance between 2 points, and that would give you that covariance matrix. The reason we choose the Matern is it's very flexible, and you can actually interpret the parameters themselves. Oftentimes things like the RBF are too smooth. The RBF is actually the limit of the smoothness parameter multiplier here. So it's sort of a more general class of functions. So the problem, just to show you in terms of math, is when we have a large data set, so this covariance matrix K is the size of your data times the size of your data. Now, if your data is anything larger than maybe on the order of 10,000, your laptop will start to fail when you try and form that matrix or try and invert that matrix. So in order to do a traditional estimation, we would do maximum, we would fill in all these parameters into the likelihood function here and repeatedly estimate them, repeatedly evaluate them in order to get their estimates. Unfortunately, this is just much too expensive. Getting this inverse and determinant is order n cubed, and even storing that matrix may be impossible when we're talking about 100 million times 100 million. And it doesn't parallelize very well to parallelize an inverse of a very large matrix. Okay, so even if we're ignoring that fact, if we're only doing predictions, we still need to do this inverse, and maybe we can do it somehow without forming it by some smart function. And if we were to do that, we still would have this O(n) squared problem. And so this tends to be untenable, and this is generally the reason Gaussian processes are not used on these large problems. So when I tell people that there's too much data, we can't form the whole maximum likelihood estimation, the first thing people ask is, well, why don't you just downsample your data and use a small bit of data that you can and call that a day? Why are we spending so much time estimating this? And the reason is that purely batching in a very simple sense does not necessarily work very well here. Of course, this is the first thing the literature tried years ago, but I just want to explain to you why. So the first sort of approach one could take in batching points, and this has inspired some other low rank type methods in Gaussian process models, is instead of using all the data, I'm just going to randomly sample the data across the domain, and then I'm going to only use those sampled points. And those are what I'm going to estimate my parameters on. The problem here is that you're making your points artificially distant away from one another. And actually in Gaussian process models, it's getting the correlation function right around the distance being 0. So it's all the local information that's going to get you the best solution. And so here you're artificially, because you're making your points more distant apart, you're guaranteeing you're not going to observe any of those very close distances, which essentially means that you're maybe estimating the whole function on a whole correctly, but not the area that makes the biggest difference in your predictions. Another approach to this is, instead of taking the points across the domain, maybe we just take a random block. The problem here is that your data, well, one, when data comes from a Gaussian process model, it's all correlated. So when you're taking a small sample that is all known to be very correlated, you're not getting a good snapshot of the entire domain. So even if the correlation function that fits very well in this domain is something, it might not be the global optimizer by any means, whether that is naturally due to the correlation or whether that is due to non-stationarity in the domain. So our sort of method, we are going to use batching, and I'll explain how it's a little bit different, but we incorporate sort of a combination of both of these things at the same time without losing. So we're going to take points across the domain, so they're going to be less correlated, but we're also going to include data that is very close so that we don't lose that information. What is MuyGPs? I've referenced it a lot of times, and clearly it's based on doing something nearest neighbors tied to doing something fast to try and estimate it. Now, there are a lot of GP methods that do this, and I'll make it clear how they're potentially different, and I'd love to have further discussion on this if people are still unsure. But the general idea here is, unlike some methods where we're going to be approximating the kernel, changing the model, we're going to assume that we actually have this global stationary Gaussian process model. This will make sure that the uncertainty quantification, and we could check all of the assumptions that we've made. We're not abandoning that globally model. We're just going to make an approximation to it. So the second thing is, instead of using maximum likelihood estimation, we're going to use some sort of loss function. And so particularly, we found like a leave one out sort of structure works very well for this. I'll describe this a little bit more in detail in the next slide. The third thought is that when we're doing these leave one out cross validations, instead of using the entire domain to make each prediction, we're only going to use the nearest neighbors to each point to get the prediction at each location. Now, this is a little bit different than maybe covariance tapering, where you just assume the matrix itself, or there are other versions where you assume that the inverse of the covariance matrix is sparse. We're actually assuming the matrix, the Kriging weights themselves. So the matrix times the matrix inversion, the vector of values that you're going to hit with the true data is where the sparsity lies. The general idea, let's say that this is temperature data. It's a benchmark case, which we'll show you the results for later, but I just want to demonstrate the method a little bit more clearly. So let's say that we're trying to estimate the model from this training data, which is temperature data of land surface temperatures from a satellite. So we'll batch some points across the domain. Here I'm only showing 5. In reality, this would be thousands, and it would be quite densely sampled. So these are our batch locations. And so then with each batch location, we would do a function where we would evaluate the loss compared the nearest neighbor, a model building the nearest neighbors and itself. So if I was going to use, let's just say, a simple loss function like root mean squared error, I would compare predictions from the colored points to each star and compare that difference. Okay, so just because this is a little bit unclear, because there are, again, like I said, a lot of methods that demonstrate this, I just wanted to put a little notation in this. We don't need to go through this too soon. I'll give my slides so that people can review them later. But the idea is that we get these local estimates of the prediction mean and prediction standard error, and then we throw them into some optimizer function. Now, people get really caught up on the fact that the function that I present first is maybe like root mean squared error, which is maybe more typical in machine learning, where there isn't an estimate of prediction variance. And they're like, hey, you're trying to estimate covariance parameters based off of a mean. The reason that this works is because the mean function itself, the predictive mean, has these covariance matrices in them. So given that your assumptions are true about your Gaussian process, it works pretty well, and you do have the sensitivity to try and estimate at least some of the parameters there well. The main approximation that we're making, so we're estimating something more like a machine learning model, and we're making one small approximation in using local data instead of the full data. These are the two things. They're both very simple. Both have been done in other contexts, but this framework we've found just works very, very well and can scale and be distributed in the way that we need it to be for this problem that I motivated. The first thing we want to check is how well does this local approximation work? And so the root mean squared error, so like the predictions we're getting from this model, if we're using a small neighborhood as opposed to the entire data set, this is just in a simulated example. Clearly, by the time we've reached about 200 nearest neighbors, we have never found that we really need to go any further than that. And so if you're thinking about data that's a size 100 million versus 200, that's an extreme sparsity that really, really helps with this computation. Further, you can see that although we're going to scale basically quadratically in neighborhood size, because of this batching extra bit, I'll show you later our timings, but it scales nearly linearly in actually when you hold this fixed in terms of scaling it. And so we like to think about picking the neighborhood size. You do have to select the neighborhood size in order to run it. Something as how willing you are to put computation into your system. So for example, if you're going to run something on maybe an edge system, you have very limited supply of computing, maybe limited resources, or you're just beginning to train something, you might want to do smaller neighborhood size. And while you're getting your final model, you might want to do something larger that will take more computation. So the other thing that we are doing clearly is we are selecting a proxy for the multivariate normal. And there are lots of ways that lots of loss functions one can consider. And I'd love to have a whole hour just to talk about this, because we've done a lot of work this year looking into different functions and how that impacts how this behaves. So the first column you're going to see here is the maximum likelihood estimator. And I've done this on a small enough data set where I can actually do this. So you can get the exact best case scenario of doing the estimation correctly. So some of these loss functions tend to do a little worse in terms of picking our MSE, but some of them perform non-significantly differently than actually just doing a true MLE, and they're able to scale. So although we may be taking this shortcut, in general, these tend to work well. And I'd love to talk details of these in the future. So when I motivated this problem, I not only, to this point, I've only talked about MuyGPs in a regression standpoint, where we have some continuous input that I'm trying to predict. MuyGPs can also be used in all sorts of other interesting perspectives, where basically we're assuming the continuous Gaussian process function is not what we're assuming, but it's some latent function. So this is how it works in terms of classification. So if I were to try and predict whether the stars or galaxies images were stars or galaxies, I wouldn't want a continuous function of non-meaning. So basically the way that this works is you assume there's some latent continuous value, and then you threshold it so that all values that end up above a certain value are given one class and below a certain value are given the other class. So this is just a visual demonstration of that, where the dots and the triangles are our two data sets. And this is just 1D just for example. And so then the dotted lines here are for different parameters, what this Gaussian process smoothing might look like. That's the general method. So let's talk about a few benchmark cases that we've prepared. So the first one is this temperature data from a satellite, from the land surface temperature from the MODIS satellite. It's a benchmark case, and it originally comes from this Heaton data set paper, which if you haven't read this paper, it's a really good description of a lot of these competing Gaussian process methods, all in the literature. What was so great about this paper is they took this data set and they blindly gave it to actually the real creators of most of these methods, so that there was no miscommunication, there's no possibility of not implementing the method the way that the authors would have. It was this big bake-off on several statistics, two of which are computing time and root mean squared error of the values that they had left out. And so it was meant to be temperature artificially sparsified by cloud cover from another day. So it was a realistic cloud cover, but we knew the truth. So the idea here is we implemented MuyGPs just blindly on the same method with very reasonable defaults. So MuyGPs, of course, has this dependence on the number of nearest neighbors that we've selected for it. So over here, you could pick something to be faster, but less accurate. And that is this point here on the left. But down on the right, you can actually get the most accurate solution with a reasonable amount of computing time also from MuyGPs. So we sort of span this ideal corner where you can select which of these things are most important to your analysis. And so these were old results. This paper's been out for, I want to say, about a year. But recently we've used different, in these new loss functions that we're exploring, we've been able to get much better solutions even than what are listed here. So a much more accurate solution in less amount of time than any of these methods. And our architecture, these were original comparisons to the paper, was a little bit less good actually than their timings should be a little bit faster than ours in terms of architecture. We were quite pleased by this, and this method is actually what got us going. We looked then in this data set, there's about 100,000 training points and about 50,000 testing points. This was just an example. I used several mean functions. I looked at all the statistics they looked at in that paper, and it only takes about 45 seconds as of this point. Thus, since then, we've done some accelerations in the code, including a GPU acceleration and a distributed version, both of which speed this up several times over. But at this point in time, this was sort of an extremely fair comparison to the amount of engineering that they had done in these other methods. And so we were much, much faster than anything else. Another scenario exists where when we've presented this to machine learning audiences, they understand that we could train our Gaussian process very fast, but actually the bottleneck was in the predictions. So most of our computing time of that 40 seconds was not in fact training the data, but instead was doing prediction updates. And the reason is that we still have to invert these matrices of the size nearest neighbors, having to do with each thing to get predictions and their covariances. So we wrote this paper earlier this year where instead of putting all this burden on the predictions, since the structure of these predictions is sort of a matrix times a matrix inverted times the data, we can approximate the matrix inverted times the data, which would still be ON to store. And so instead, since that part of the equation does not really change unless you have new it does not change for any values across the domain. If we do some approximation to this as part of the training process, then our predictions can be much, much faster. Now, because we have to approximate this in slightly of a different way than we've approximated the rest of MuyGPs, we do lose a little bit of accuracy compared to what we expected previously. So these results in RMSE and prediction time are on the same data as what you just previously saw. But the prediction part of the problem, which you might need to do repeatedly. So let's say you were doing a Bayesian calibration and you used your surrogate model and you were trying to repeatedly update it, or you were doing reinforcement learning where you were trying to repeatedly call that same surrogate model. So both of these are scenarios where you would need predictions from the model very fast rather than the training of the data to be very, very fast. And so in this case, we're very competitive with most of these other state-of-the-art known as fast GP methods from GPyTorch, in addition, a neural network. So our method was much, much more accurate. So it can retain, although it lost a little bit of its accuracy compared to doing MuyGPs in the previous way, we were also able to stay competitively in terms of this online prediction time. The last example benchmark I want to show you is based on another famous benchmark known as the borehole function. And so the general idea here, it's a little bit higher dimensional than the previous benchmark problem, but instead it's also anisotropic, where you need to do some sort of deformation in order for the stationary Gaussian process model to be a good assumption. This has been used for quite some time. And so you can sort of see how exciting and how much change there has been to Gaussian process models in recent times. When we look at some of these, so this is a borrowed paper from this other Bobby Gray-Massey paper, where previous methods got RMSEs at the same data size, about 1 or something near thereof. But more recently, these models have been able to achieve closer to 0. So the examples here, we were able to fit both a stationary Gaussian process model and MuyGPs with some deformation and able to achieve better results than were previously published. Yes, is there a question?
Yes, Dr. Muyskens, there's a question. How do you choose what parameters?
They're evaluated through doing this leave one out, comparing the truth to what is predicted in the model, this cross-validation metric. And that's the entire point of MuyGPs, is to get these hyperparameters as best we can. I apologize, I lied. There's one more problem, although I would not consider this a bad benchmark problem. This was our originally motivating problem. And so we're trying to take these images, these cutouts of stars and galaxies to automatically assign these as being either a star or a galaxy. And sometimes they're easy to tell, like maybe we can tell this top image is different than this bottom image here. But another example is the second point that I've shown here, and they look very much like the alternate class. We made a similar data set actually for some students that we're working with, and they were very disappointed they couldn't tell the difference by looking at them. and I laughed. I said that's the entire problem, that if we could just look at these and know what they were, it would be a very, very simple classification problem. But instead it's very difficult. This is an astronomy point, just for any of anyone in the audience that's interested. In addition to including an image itself, we had images of different filters, and in addition, point spread functions, which basically means instead of having just an image of data, we had a cube of data, which just basically raises the dimension of your problem. In order to accommodate this, prior to putting the data into the Gaussian process model, we did do a PCA decomposition. This is not necessary, and actually we have done this in other ways where we fit like a neural network as sort of an autoencoder idea to embed the data in a lower dimension. You can actually just fit it on the pixel space, but with a small normalizing correction. There are all these different ways you can do it. But as you can see, as the PCA components get larger, you get the more galaxy-like features that are the further away and less symmetric data values. And so the general idea is we're going to put in then it's a size about 50 problem. So we compared our method to a CNN dense neural network, also on that PCA reduced data, so that we weren't helping ourselves in an unfair way doing that data reduction, or logistic regression, and MC, which is morphological classifier, which is the way that astronomers look at this data. And generally they look at how symmetric that blob is. And based on the symmetry or lack thereof, they try and classify it as either a star or a galaxy. And this is sort of the way in general they've done this in the literature without machine learning. So when we have a very limited training sample size, we see that the Gaussian process model, even with all these approximations we've made, does much, much better than any of the other models. But when the training size gets very, very large, you see that the scaling in that training size is very, very poor for a CNN, meaning that it has this nearly cubic scaling that we would not necessarily need, be able to support retraining these models on these very, very large data sets. However, our model, due to the approximations we've made, does a very good job at keeping this training size. It looks flat. It's very, very, it's linear with a very, very low slope. The last thing we did with this is looking at, then we gave the model maybe a fixed amount of training time. So we cut the CNN and GP off after a short amount of training time, and we looked at how the models performed. This was meant to represent, like, we had limited power, we were on an edge system, we could only train for so long given the amount of data that was coming in. And of course, in this case, since the GP takes so much less time to train, it performed way outperformed the CNN. Of course, since the CNN was not nearly done. Unrelated to what we have been talking about, but there's this extra promise of more robustness in the GPs. So unlike a neural network, which will overfit and have these large number of parameters, we can actually interpret, and what the GP tends to be looking at, it tends to be something that is more related to human features as opposed to neural network features. So one of the big concerns in the neural network literature at the moment is that you can take, maybe you've seen this, you can take an image and add an imperceptible amount of noise to it, to the human eye. So maybe it's a panda, and I add some amount of noise that we can't tell the difference on. And now the classifier classifies it as a school bus. And obviously this is ridiculous to us as the features that we look at, but obviously not for the neural network. So one type of attack that can be demonstrated on this is called FGSM attack. And so what I'm showing you here is on the MNIST handwriting database. So the idea here is it's a data set of handwritten images, and you try and classify what image, what numeric they were trying to write. So with a CNN, you generally get a little bit more accuracy than maybe you do using MuyGPs, again, with no PCA. This is just on the pixels themselves. But when you start to look at that there's been an attack, and the attack is targeted towards the CNN's architecture. So this is a little bit of an unfair comparison, but the idea being that that same attack would not work on the Gaussian process in the same way. It's much more robust to these attacks. And so we see this potentially as not only a reason we should trust the Gaussian process more, and again, this is just a very early prototype of this sort of thing, but potentially we could use, because it's so lightweight, something like MuyGPs to augment systems that already exist and make them more secure. What I promised is that MuyGPs and the project that we're working on currently is a 3-year project. We've just completed our first year. Our goal is to take what is currently a stationary version of MuyGPs. You may have noticed we use the matern parameters, but there's nothing in the way that the method works that necessarily requires it be that kernel. You can put in any kernel function that you know and love. We've fit this with periodic functions. We've done some other types of kernels, but you can also fit these non-stationary kernels. Now, the only complication here is that they tend to be higher parameters, which just means that you might need more batches in order to train it well. So we have some specific ideas, and I could talk about this all day. I'm very, very excited. These should be implemented in the next few months. Of some sort of classic non-stationary models that work very, very well with this framework and can still be distributed in the MuyGPs framework. Now, the first idea is sort of deformation models. And so the way these models work is instead of putting in just the typical 0-1 cube data into your stationary Gaussian process, you need to deform that space, that input parameter space, prior to putting this in. And so like I described, we did this with a PCA, but one could imagine doing this all sorts of ways. And we have done this with a neural network, with some other known deformation models. And this also leads to the idea of one could even do with MuyGPs a deep GP, where it's a neural network of Gaussian processes that are all trained with this local function, which would just make them insanely more practical, which we have not done that yet, but I'm very excited at this prospect. So another type of model that one could imagine in the non-stationary space are called hierarchical models. And so these models, instead of having one set of parameters in the stationary matern that are good across the domain, we assume that there's this like Bayesian hierarchical model where the parameters themselves, the hyperparameters, maybe the smoothness or the range parameter in the matern, vary across the domain themselves. In this case, you basically want to set up some goalposts. Maybe we assume that it's a low rank Gaussian process just for simplicity, since it's going to be something very smooth. It shouldn't make much of a difference, but we estimate those parameter values at these not locations, and then that gives us via Kriging the values at every other location. So that's a way to make this problem tractable. Of course, you can do it fully Bayesian using MCMC, but that's never going to be nearly fast enough for the applications we're looking at. A final idea that we have is to consider a spatially varying mixture of these stationary Gaussian processes. And we believe that we'll be able to do this similarly using MuyGPs. And there's tons of other ways that this can be. If you're interested in exploring any of these domains or some other idea with MuyGPs, we'd be happy to talk to you and work with you and see the packages ongoingly. Like I said, for 2 more years, we have the funding to work on it. And so there's all sorts of things. We have a very small team, but there are infinite directions in which this could go. Oh, I just also want to mention, instead of, I've only shown you univariate data, but we've also done this for multivariate data. And that especially came into play when we were looking at these dark matter simulations. The reason being the parameters of dark matter are not independent. So when we wanted to look at confining them, we needed to look at a multivariate distribution. And so MuyGPs worked relatively well in that scenario. This is just showing you, we've also done some accelerations. We've done GPU accelerations in addition to MPI implementation, which is distributed for high performance computing. So those the high performance computing should be released in the next couple of weeks, but you can choose when you're running MuyGPs based on your architecture, which of these scenarios you would like to describe. So should it be GPU accelerated? Shouldn't it be MPI distributed? What would work best for the architecture you're trying to run MuyGPs on? Our computer scientists have done a fantastic job making this very accessible, and I'd love to help you get going on it if you are interested in trying this, although there are tons of examples online with our package demonstrating this. So again, this code is available and released, available to download today. You might not be able to see all of the features that I've talked about today, but they should be coming in the next few months. We've published a host of papers, most of which are on archive, so you can access them quickly. And I think that's all that I have to say. Thank you for your attention.
I'd like to thank Dr. Muyskens for taking time to share the research that you and your team have done so far. I will put up one more slide with Amanda's information. And if you're interested in presenting at a future webinar, feel free to check out the SDNS community website. And one more thing, SDNS is soliciting entries for the section's student paper competition for next year's JSM. This competition is open to all undergraduate and graduate students, as well as researchers that are at least 2 years beyond their terminal degree. We request that entries be sent to Kim Caulfield by mid-December.